Hey guys, welcome back to the second video of the building styx series. Today's topic of discussion is bencode. So without further ado, getting into it. First question, what is bencode? Well, like the way we use JSON to encode metadata for most of the things we use in software engineering, bencode is in some oversimplistic terms JSON's cousin in a sense of speaking. So like bencode is the thing we use in the torrent world to encode metadata. And not just metadata, practically a lot of things are done using bencode. So for now, just understand this, that the files that need to talk to each other, the peer-to-peer interaction, tracking files in swarms, in like identifying which file is it in fact. Because see, in while using torrents, there are so many peers and seeders involved that the client doesn't trust them inherently basis on just because of the fact that they have a torrent file or they are seeding it. They need to agree on something. Like for example, I need a particular piece of a particular movie that I'm downloading via torrent, and there is a long list of particulars. So how do you agree on that? You agree on that via metadata. What do you use to encode that metadata? You use bencode. That's it. So, okay, now I know what metadata is, but what does it look like? So, metadata has four types: integers, byte strings, lists, and dictionaries. Let me explain. Integers are self-explanatory. The format of writing an integer is to start with I and to end with E, and in between you will write your base 10 digit. So as you can see by these three examples, I42E will be just 42. I minus 7E will be minus 7. I0E will be 0. So let's say if I write I69E, that is 69. Coming to byte strings. So byte strings is basically, in byte strings, first we have to declare how many bytes the string is gonna take and then write the string itself. For example, you can see 4 colon spam. So it will take 4 bytes and then there's a 4-letter word. So it's taking 4 bytes. If for hello world it's 11. For 0 it's like this. The number prior to colon tells how many bytes to read. Then there is lists. It works similarly to integers. Whereas integers began with I and ended with E, this begins with L and ends with E. But since list is a container element having a lot of elements, so it contains, like it can take input for byte strings, integers. For example, here you take the word spam, then you take the number 42. So it reflects here like this. Then there are dictionaries. This begins with D, ends with E, and a collection of key value pairs basically. There are two rules for dictionaries, by the way. One, that each key must be a byte string and they must appear in lexicographic order. Lexicographic order is a fancy word for being like alphabetically arranged, sorted basically. So that's that. I'll explain these two rules later down in the video, but for now just take them at face value. So another question is, since we are making this client in Rust, how can we make sure that uh, we have a certain type which can, take input of all of these types? So in Rust, that comes out to be called as an enum. And enum is a thing in Rust. I won't go too much into the details, but it's a type in Rust which can take input of many other types. So this is perfect because I can make an enum called bencode value and have it accept 4 kinds of values. Integer is a simple one. It's a 64-bit signed integer. Lists are just a vector which will grow according to the bencode value. It's very self-explanatory. So the next thing that comes to mind is bytes, byte strings. Well, if you noticed, we were working with strings there above. Here we are working with strings, but I'm taking its input type as a byte. Why is that? Well, the thing is that a bencoded string is not always readable by humans. Sometimes it's just raw binary data. For example, torrent piece hashes. Every piece of a torrent has a unique hash which the client verifies against. Now that hash isn't readable by us, it's raw binary data. So if I force it to be a string, I'd be forcing UTF-8 validation on a protocol that never promised UTF-8 validation. And that will either lead to the client rejecting it outright or ugly workarounds all around the whole project. So that is why we just settle for bytes, as it's the most simple, basic truth of any information there is, that even a human readable text is bytes at the end of the day, and raw binary data is also just bytes at the end of the day. So we can all agree to this. That's why we chose bytes. Dictionaries is just like lists, growing a growing list of values. But the more important, interesting part is B-tree map. You don't need to know a lot about B-trees. It's just a data structure which takes values in a sorted order always. So like if you remember the rule that I mentioned here, that keys must be byte strings and must appear in a lexicographic order. So this ensures that whatever whatever manner I take inputs in, it's always sorted. So I won't have to worry about manually sorting it later. So that's that. And yeah, after doing this, the public API turns tiny and it just becomes two functions, which are decode and encode. Decode takes raw bytes and makes them into a bencode value, and encode takes bencode value and puts them into raw binary data. So the next question is, okay, now I know what bencode is, how it looks, how it functions. What if my parser fails? I'm writing a bencode parser, what if it fails? So a very shitty kind of error would be getting parse error, because this doesn't tell me anything about why the parser failed or where specifically it failed. So the best kind of errors are always the most specific ones, like invalid byte string length. So let's say if someone wrote x hello. Sorry. Yeah, wait. Yeah. What if someone wrote this? Now x is not a valid byte string length. We need numbers here. We need 5, we need 6, we need anything but a letter. We don't need letters here. So that's invalid. Now if I get an error like this, I know exactly where to look. If we get byte string out of bounds, we know that someone allocated more bytes but gave less amount of bytes in the string here. So that's that. We get an invalid integer offset for 128. So like I know that at an offset of 128 there's an invalid integer somewhere uh, in whatever field this error is in. So this tells me important info. So that is why specific errors are very important. This is something I learned while writing the parser. So this was important information. To the next topic. It's a very interesting question actually. Let's say if we write I3 and I03, are these two different? Take 5 seconds to think about it and tell me what you think about this. Time's up, I think. Yeah. So if you remember, I3E was just a way of representing an integer. So this is 3. And I03E was also a way of representing an integer. So essentially this should be 3. 03 to be precise, but for us it will be 3, right? 03 is equal to 3 for us, but for torrents 03 is not equal to 3. So to understand why this is not the case, you will need to understand how BitTorrent, like the torrent clients actually verify what piece of torrent they're working with is. in any torrent client, the torrent client hashes the raw binary bencoded metadata, like like whatever bencoded data they get, they hash it. Now, I don't know how much you know about cybersecurity, but hashing is a way of, in the most simplistic terms, hashing is the way of jumbling up info and encrypting it in a way that you can't read, like you don't know what the hell was here as actual data, but after hashing it will turn into some unreadable stuff. For example, let's say I want to hash the word apple. Apple will become some gibberish. Okay, that's it. That's it. Like in the most simplistic terms, without going into what hashing actually is, this is what hashing is. So in order to hash something, the order of it matters a lot. If I change apple, if I reverse my writing, if I reverse the word, if I write ELPPA, I will get a drastically different hash here. And why did it get a different hash? Because I reversed the word entirely. So hashing is extremely sensitive to the sequence of characters that it is actually hashing, which is why 3 and 03 won't be treated the same way. Because let's say I am hashing a torrent with, like I'm hashing an information which has been coded data 3 and one which has 03. This will lead to a different hash. This will lead to a different hash. Now the torrent client is stuck. Torrent client thinks, oh wait, you were the piece representing, like let's say this is an identification thing. So you represented 3. Okay, you were from this show. Got it. You're 03. Wait, you are from a different show. Even though to our eyes this looks the same, just because of having that 0 here, the hash will be totally different and the torrent client will identify it as a totally different thing. Which is why we come to the topic of canonical encoding. Canonical encoding. Canonical means each number gets one valid spelling, that's it. So if I want to express 3, the only way to express 3 is I3E. That's it. No, like you can't express it as, wait, you can't express it as I03E or I003E. None of that will work. The only correct way of expressing it is I3. So that's that. So this is another type of error that you can encounter if you're not paying attention to this. Now, there's another thing that I learned a lot was validating before you even work on the parser. So all of the errors we saw prior to this are errors that you get in the output. But obviously we want to make sure that before we even take any data, we can know that the data I'm taking is pure in a sense of speaking, like whatever data I'm taking is correct, so that I don't have to deal with this shitty output I get all the time after the parser is done with it. So the best way to ensure that I don't get shitty or bad output is to make sure that I'm taking good data. So to do that, you'll have to put some checks and stuff in there. Example, let's say I have a dictionary. It has name and size as key value pairs. Name is this, size is this. After encoding, there are two cases. Case A, where the name and size are presented like this. B, where they are reversed. What do you think will happen? These two will obviously have very different identities. This is a totally different thing and this is a totally different thing. So because of having a different byte order, they'll have different hashes, and because of that, they'll have a different torrent identity. So that is why it's important to validate before we touch any info, that, okay, it's in the format that we want. It's not in a wrong format, so to speak. Now, this is all of this was about bad input or bad output. What if input is correct? Can the output still be bad? It can be. I'll tell you how. Let's say if you remember, L, E, and anything in between is used to represent a list. Let's say I write Li1 E E. So that just represents 1. If I do this, it's the list value of 1 inside a list. So a nested list basically. I do this, it's a double nested, and so on and so forth, like this. It can go deeper and deeper, as deeper as it wants to. So in a recursive parser, like how a recursive parser works is, it parses the list and it calls upon itself again and again and again, as many times as it needs to. So the problem is, the deeper you go, after a certain point, there will be stack overflow, and client is dead. The client will stop working. So to prevent this, now this is exactly what I'm talking about. Validate before you touch. This is extremely important. So to follow that validate before you touch principle, we will define a max nesting depth of 512 bytes. And if depth is greater than 512, we will just return an error of depth limit exceeded. That's it. Because realistically, no amount of bencode metadata will be listed greater than 512 bytes. So this is another way of preventing bad data. Preventing bad data is, for example, you get an input of bencode data like this, I42E, I99E. Now, I42E is a valid value. A lot of parsers they will say 42 is check, and then they will just leave it. Nothing. But our decode function is built in a way that it will either take the whole input or throw an error, because this leftover data is dangerous. Leftover bytes, you haven't identified it, you haven't parsed it, it's dangerous, right? So this is another way of preventing disaster, so to speak. Then comes the topic of testing, which is unit tests are the tests that I like. Basically, the input I can think of. Property test are machine invents the whole data, and the stress test philosophy behind it is to go through the whole cycle of value encoding, decoding, and then arriving at the same value again. As long as we can do that, the parser is working as exactly as we want it to. And the ideal behavior we expect is that if we throw in random bytes, we get decoded value, and upon that it can either give an okay, so that means decode succeeded. It can give an error, it means it failed somewhere. But panicking is a problem, because uh, why would a parser panic on random bytes? If it's panicking on a random byte, which means we went wrong somewhere in its construction. As long as we can get a mistake or an error which is specific and which doesn't break the client entirely, we know where to look. But panicking is wrong. That usually means a stack overflow or something like that, which is extremely risky. So yeah, that was that. It's a small concept, but the entire thing is important if you're going to proceed with building the BitTorrent client. It's an extremely important concept. The entire stability of the system is built on this only. Since this is the language, the entire torrent client and peer-to-peer messaging, everything, this is the language they deal with. So that's all. See you all in phase 3. We will come back with wire protocol and network and stuff like that. I'm yet to write a blog on those. So I think first I'll write the blog and then we can discuss what we will do with the video. We'll see.